Programming languages are the tools that allow us to give instructions to computers. They serve as the bridge between human logic and machine execution, enabling us to create software that can perform a myriad of tasks, from simple calculations to complex simulations. C is one of the most powerful and versatile programming languages ever created. Developed in the early 1970s, it has stood the test of time and remains a cornerstone in the world of programming. Its syntax and structure have influenced many modern languages, making it a fundamental skill for any aspiring programmer. It's known for its efficiency, speed, and close to the hardware capabilities. This means that programs written in C can run incredibly fast and can be optimized to use system resources very effectively. This is why C is often the language of choice for developing operating systems, embedded systems, and performance-critical applications. Learning C is like learning the fundamentals of how software talks to hardware. It gives you a deep understanding of how memory management works, how data is stored and retrieved, and how different components of a computer system interact with each other. This knowledge is invaluable, not just for writing efficient code, but also for debugging and optimizing existing code. C is used in a wide range of applications, from operating systems to game development. Its versatility allows it to be used in various domains, including scientific computing, financial systems, and even in the development of compilers for other programming languages. Its influence can be seen in many other programming languages. Languages like C++, Java, and even Python have borrowed concepts and syntax from C, making it a foundational language that can help you understand and learn other languages more easily. Understanding C opens doors to a deeper understanding of the world of computers. It equips you with the skills to tackle complex programming challenges and provides a solid foundation for learning more advanced topics in computer science. If you're interested in a career in software development or just want to understand how software works, learning C is a great place to start. It not only enhances your problem-solving skills, but also gives you the confidence to explore and master other programming languages and technologies. Its concepts and syntax form the basis of many other languages. By mastering C, you gain a deeper appreciation for the design and architecture of software systems, and you become better equipped to write efficient, maintainable, and scalable code. C programming empowers you to create efficient and powerful software solutions. Whether you're developing a new application, optimizing an existing system, or contributing to open source projects, the skills you gain from learning C will be invaluable throughout your programming career. C has a rich history, dating back to the early 1970s. During this era, computers were becoming more accessible, and the need for a powerful yet flexible programming language was evident. It was developed by Dennis Ritchie at Bell Labs, a place renowned for its groundbreaking work in telecommunications and computing. C was initially designed for use with the Unix operating system, which was also a pioneering project at Bell Labs. Unix itself was also being developed at Bell Labs around the same time, and the synergy between Unix and C was instrumental in their mutual success. C's close association with Unix is one of the reasons for its widespread adoption. The language's ability to interact seamlessly with the Unix system made it a favorite among developers. Unix, known for its stability and power, became a popular choice for servers and workstations. Its robustness and reliability made it a cornerstone in the world of computing. As Unix spread, so did C. The language's portability allowed it to be used on various hardware platforms, further cementing its place in the programming world. C's simplicity, portability, and efficiency made it an ideal language for systems programming. Its straightforward syntax and powerful features attracted a wide range of programmers. It gave programmers a lot of control over hardware resources, enabling them to write efficient and high-performance code. This made C well-suited for tasks like writing operating systems, compilers, and embedded systems. Its influence can be seen in many modern programming languages, which have borrowed concepts and syntax from C. The legacy of C is profound, as it laid the foundation for many contemporary languages like C++, Java, and even Python. Its impact on the software development industry is undeniable. Today, C continues to be a vital tool in the programmer's toolkit, used in everything from operating systems to game development. Its enduring relevance is a testament to its robust design and versatility. As technology evolves, the principles and practices established by C will undoubtedly continue to influence and inspire future generations of programmers. Every C program follows a specific structure. This structure helps organize the code and makes it easier to understand. Think of it like building a house. You need a blueprint to guide you. A typical C program consists of several sections. These sections work together to form a complete program. Understanding the purpose of each section is crucial for writing effective C code. Let's break down the basic structure of a C program into its essential components. Each component plays a specific role in the overall functionality of your code. By understanding these building blocks, you can start constructing your own C programs. The documentation section is like writing comments in your code. These comments are not executed by the computer. Instead, they serve as explanations for anyone reading the code. Good documentation is essential for making your code understandable. It helps others, and even yourself later on, to grasp what the code does. Imagine trying to understand a complex machine without any labels or instructions. Comments can be single-line, starting with E, or multi-line, enclosed between, and use them to explain the purpose of your code, describe variables, and clarify complex logic. Section 5. Linking. Connecting the dots in your program. The link section is where you include header files. Header files contain pre-written code that provides access to useful functions. Think of them like toolboxes. You don't need to invent every tool yourself. For example, the header file provides functions for input and output, like for displaying text on the screen. By including this header file, you can use these functions in your code. The directive tells the compiler to incorporate the contents of the header file into your program. This allows you to use pre-built functions and data structures, saving you time and effort. Section 6. Global declarations. Setting the stage for your variables. In the Global Declaration section, you define variables that can be accessed from anywhere in your program. This is a crucial step in setting up your coding environment, as it allows for a more organized and efficient workflow. These variables are like global settings that apply throughout your code. Think of them as the backbone of your program, providing essential values and settings that multiple functions and modules can rely on. For instance, you might declare a variable to store the value of pi, which is 3.14159 here. This is particularly useful in mathematical computations where the value of pi is frequently used. This way, you can use this value in different parts of your program without having to redefine it every time. It ensures consistency and reduces the risk of errors that might occur from redefining the same value multiple times. However, global variables should be used sparingly, as excessive use can make your code harder to manage. Over-reliance on global variables can lead to code that is difficult to debug and maintain, as changes to a global variable can have far-reaching and unintended consequences. It's often better to pass variables as arguments to functions, which we'll discuss later. This approach promotes better encapsulation and modularity in your code, making it easier to understand and maintain. By passing variables as arguments, you can limit the scope of their impact, reducing the likelihood of unexpected side effects. In summary, while global variables can be incredibly useful, they should be used judiciously. Proper management of variables is key to writing clean, efficient, and maintainable code. As we move forward, we'll explore more best practices for variable management and how to effectively use them in your programming projects. Stay tuned. as we delve deeper into the world of variables and their role in creating robust and reliable software. Section 7. The heart of the action, the main function. The function is where your C program begins execution. It's the entry point of your code, like the front door of a house. Every C program must have a function. Inside the function, you write the instructions that you want your program to execute. These instructions can include calculations, input-output operations, and calls to other functions. The function typically returns an integer value, 0 for success, other values for errors. This value can be used by the operating system or other programs to determine if the program ran successfully. Section 8. Subprograms. Breaking down tasks for efficiency. Subprograms, also known as functions, are blocks of code that perform specific tasks. They help break down your program into smaller, more manageable chunks. Think of them like specialized teams within a company. Functions promote code reusability. Once you define a function, you can call it multiple times from different parts of your program. This avoids code duplication and makes your program more organized. Functions can take arguments, which are inputs, and return values, which are outputs. This allows them to communicate with other parts of your program and perform specific actions based on the data they receive.